Hi there. In this lecture, I want to talk more about the ocean. The lecture has two parts. The first part is an overview. I want to discuss the impacts of the ocean on the climate. I want to talk about surface distributions of temperature and salinity. Okay, the surface temperature distribution have a direct impact on air temperature and climate on Earth. I want to discuss surface currents, the vertical structure of temperature and salinity in the oceans, and the thermohaline circulation. Okay, and surface currents and the thermohaline circulation have an impact on climate. Okay, on regional scales. In the second part, I want to discuss ocean carbon pumps. It's about carbon, it's about CO2, and the internal cycle of CO2 in the ocean. Okay, and I also introduce you to air-sea gas exchange. We talk about the solubility and the biological carbon pumps. We look at the dissolved CO2 concentrations in the oceans. And we also look at regions where actually plankton is created, okay, which involves a conversion from inorganic into organic carbon. All right, alrighty-o, let's get started. And we start with an overview. Okay, I give you a list of ocean features, the impacts of the ocean on the climate. First of all, the existence of the ocean leads to milder continental climates. Yeah, it's to do with the transport of in so-called warm water currents that can move warmer water into colder climates, but also the general heat buffering effect of the ocean leads to milder climates. And we discussed this before. Indeed, the ocean is a key source of water vapor for the hydrological cycle. We also discussed that. And it's involved in a number of interannual climate variability processes through the feedback between sea surface temperature anomalies and evaporation. Okay. Interannual means from year to year. And we will discuss interannual climate variability in a future lecture. Okay. Seawater temperatures have influence the sea ice formation and the melting of ice shelves. And this is a big, big feature of the oceans. Okay, so if you bring warm water, relatively warm water, in contact with an ice shelf, it will induce the melting of the ice from below. It's a key feature. Well, air-sea gas exchange, there's the transfer of gases across the sea surface. It's to do with the intake and release of CO2, and that's linked to the carbon cycle. Okay. And indeed, sea level change has various impacts. Okay, the change of the sea level. All right. We start with having a look at the surface distributions. Again, we look at the surface distributions of temperature and salinity. Okay? Temperature first, and then I talk about salinity. Let's have a look at the surface temperature distribution. Here we go. And we talked about that before. You can see that there is warm water. Shown here is a scale. This is in degrees Celsius, and red is above 25 degrees. The dark red is above 30 degrees. And if you look at the blue, sort of blue is below 10 degrees and down to 0 degrees. Okay? noting that the coldest waters in the ocean are -2 degrees Celsius, around that, because that's the effect that the addition of salt has on the freezing temperature. Anyway, you can see we identified the warm pool in the ocean, which is this large area of the warmest surface waters in the oceans. Okay, and I'm not going much more into the details with that. You can see that, and we can link surface temperature to the initiation of tropical cyclones. Okay, surface salinity. Okay, it's about the concentration of salt in seawater. Okay, it's about 35 parts per thousand. In other words, about 3.5% of the weight of seawater comes from dissolved salts. Okay. Both temperature and salinity control the density of seawater. Density is weight per unit volume, how heavy seawater is. Okay? And on its own, density decreases with temperature and increases with salinity. Only on its own. In reality, it's now the combined effect of temperature and salinity that controls the density. And density is important in the ocean because density determines which water stays at the top and which water you find at the bottom of the ocean. And it's the lightest water that you find near the surface. In polar regions, it's the salinity that controls the density stratification. Density stratification, we mean what's on top and what's below. Okay, it's the vertical structure of density. Okay, so in polar regions, it's actually the meltwater which creates a low density. Okay, that means there is low salinity water on top, and this water can actually cool down to the freezing temperature and form ice. That's an important feature of the oceans. Without that control of salinity, you could never form any sea ice in the oceans. In the warm water regions, it's the temperature that controls the vertical density stratification. Here we have warm water sitting on top, and salinity doesn't matter. Okay. All right. So that's the interface to the atmosphere that you can see. The interface to the between the oceans to the other components of the climate system. All right, so let's have a look at surface currents. Okay, these surface currents are driven from the surface winds in the atmosphere. We discussed the surface winds in the atmosphere, and they create structures in the ocean, circulation structures, which are called gyres. Let's have a look here at this in this map. Okay, you can see these arrows indicate circulation patterns in the ocean, and the currents are generally much smaller than compared with winds. So we're talking about maximum speed in the ocean is something like 1 to 2 meters per second at maximum, but more generally you have 10 centimeters per second or less current speeds. So they're relatively slowly moving water masses, and these are called subtropical gyres. Okay, they exist north of the equator and south of the equator, and they exist in all oceans. In the Indian Ocean, in the northern Indian Ocean, it's a little bit more complex because we have monsoon-related wind changes, and there are the circulation changes. Yeah, there are seasonal changes. So this map shown here for the northern Indian Ocean does not apply for throughout the year. So what's now the significance of the current? I forgot to tell you that these currents, they're essentially reach from the surface to about 1 kilometer depth. Strongest near the surface, but they still have a significance at down to a kilometer. Okay. So what's now the most significant feature? The most significant feature of this circulation is that there are warm water and cold water currents that influence climate. And one of the most significant feature is a little bit hard to see here, is we are here in the northern Atlantic, in the North Atlantic, and it's the Gulf Stream, which is a strong poleward current, and actually there's an extension of it, okay, called the North Atlantic Drift, and it actually moves warm water into the Arctic Ocean. In the Arctic Ocean, it's not near the surface because it would melt all the ice. It's found below the surface, at depth between 200 and 500 meters. Okay, and it's this current which actually moves warmer water into a colder climate and leads to a relative warming. It leads to a milder climate in northwestern Europe. Okay, this is an example of a warm water current. And there on the western side of these gyres, there are these warm water currents. Okay, but the one in the North Atlantic is the most significant because it has this northward extension. Okay, you can see these warm water currents. In Australia, we actually have two. On the west coast is the Luan current, moving warmer water southward, and on the east coast we have the East Australian current. Okay, there's also cold water currents on the opposite side. Okay, cold water currents that move colder water into a warmer climate. Okay, so there's lots of action taking place in terms of heat transport in these subtropical gyres. Okay. All right, so that's the story about the surface currents. All right, so what else can we do? We look at the vertical structure. Okay? The vertical structure. The oceans have a specific vertical structure, and you can distinguish water in the ocean. Okay? And that's why you can name it. You have surface water, you have central water, you have intermediate water, deep water, and bottom water. These are the names for the different type of water masses that we find in the oceans. Okay? And we name different water masses because we want to understand how these water masses change under the effect of global warming. Okay? So let's have a look at one example. Okay, and I want to show you an example of the structure, the vertical structure in the ocean, just cutting through the Atlantic Ocean from south to north. And this, each one of these slices is a slice cutting through the Atlantic Ocean. The top one is temperature. Okay, from the surface to 5,000 meters, from south to north, showing you the temperature structure if you cut across the Atlantic Ocean. The second one shows you the salinity structure. Okay, how the salinity structure looks like, and the units are grams per kilogram here. Okay, and the third one is dissolved oxygen. Okay, the structure, how that looks like. And I don't want to go too much into detail, but one thing that you can see here is, in terms of the temperature structure, look at the yellow, orange, red region here. And this transition between the warm water near the surface and the colder water underneath in this zone is called the permanent thermocline. Okay? And this one essentially blocks the exchange between the surface and deeper water. Okay, it's a lid. It's a thermal lid that sits on top of the ocean. Salinity field, we can also see some clear structures in there. There's something we call a tongue of relatively lower salinity water that you can trace, that you can follow through the ocean. Okay? And because of these differences in temperatures and salinity, we can actually identify and name different water masses. The most important ones, as part of this lecture, is the North Atlantic deep water, which is shown here in this top one. You can see in the second one too. Okay, and the Antarctic bottom water, which is the not named here, but it is the coldest water that you find in the ocean. It's around here. It's the Antarctic bottom water. Okay, it's named here in the third graph. Okay, because that's linked to the deep circulation of the ocean. Okay. Oxygen distributions are important if you want to study so-called dead zones in the ocean, because there are regions in the ocean where there is not enough oxygen to sustain most marine life forms. Critically low oxygen levels, naturally, because of, but I don't want to talk about the dead zones here. Again, just a feature that you can identify if you study the oxygen distributions in the ocean. All right, now let's talk about the thermohaline circulation. Okay, because that's linked to climate variability. Okay, there is a deep circulation in the ocean, and it actually starts in the North Atlantic. And the North Atlantic is the key region of the formation of dense water, okay, heavy water, that is so heavy that it mixes down to the relatively deep, so that it can drive the deep water movements through the world ocean. Okay, and on this map there are formation areas. One is in the Nordic seas, including the Greenland Sea, and the other one is in the Labrador Sea. Okay, and this is where this dense water mixes and it reaches relatively deep into the water column and then drives a current that runs around the entire Earth. Okay, starts in the North Atlantic, moves into the South Atlantic through the Indian Ocean, and eventually into the Pacific Ocean. And this structure is important in order to understand the distribution of CO2 and nutrients, dissolved nutrients in the ocean. But I will come to that. The other part where the so-called bottom water is formed, the water which sits directly on the bottom, are regions in the Weddell Sea and the Ross Sea, which I illustrated here. Okay, but these waters, although they reach in some regions, even cross the equator, so they mainly move around a region which we call the circumpolar current. Okay, it's a circumpolar current. The time scale of this entire circulation is 1,000 years. That's the time it takes for this circulation to complete. It does not only have a deep branch, it also has a return flow, and the return flow is shown here in the map. Okay, and that's this important principle. If you have a water parcels moved away from an area, there has to be a return flow, at some other level. And these return flows take place near the surface, and you can see here in red the surface flows. Okay? All right, return flows. Okay, and now the importance with the link to the climate is the return flow. So we're looking now, we're moving into the North Atlantic, and there's a little sketch of the so-called North Atlantic overturning circulation. Okay, that's how we call it, an overturning. It's not much really overturning, but it's more a replacement. So what happens in this area is you have the formation of dense water, okay, through a mixing process that we call convection. Okay, let me start here. This is Greenland Sea, Labrador Sea region. This example shows the Greenland Sea. You have so-called overflows. This dense water flows around and then moves away from the North Atlantic. Okay, as deep water. Okay, and you have even a little bit of bottom water coming from Antarctic coming in that. So as this water moves away, it sucks in water near the surface. And this is the North Atlantic drift, the return flow. Warm water, as an extension from the Gulf Stream, is sucked northward, okay, and then it dives down between surface water. It actually ends up in the Arctic Ocean. Okay, and you can trace this water through observations. You know where it is, how it moves. Okay, and it's this return flow that makes northwestern Europe on average 7 degrees warmer compared with northeastern America. And I'm talking about the surface climate, not the oceans. It's that indirect impact of having warmer water in an area that makes northwestern Europe much warmer compared with the same latitude on the other side of the Atlantic Ocean. And this concludes this part of the lecture.